Hello everyone, welcome to the video explanation for Brian Passwater's topic 29 notes, example 5. Now example 5 is where we start to talk about logarithmic scaling. Okay. Here at the top we need to talk real quickly about these graphs. These are actually the same exact graph. Now on the left we have a linear scale on the y-axis. See that those are going up by 1 million people on the y. And the problem with that is you really can't tell anything about these points over here. They're so close to zero compared to a million that you just can't read any of them. However, if we take that same data and we graph it on a logarithmic scale based on the number 10, meaning that this is 10, 100, 1,000, 10,000, 100,000, 1 million, and 10 million, you can get a much better look at that data because the range of that data is so big. It goes from 1 up to, around 7 million. The problem is that data is just too big. When you have exponential growth, it's really difficult to graph that with a linear scale. So what we're going to do is we're going to graph it instead with a logarithmic scale. This is called a semi-log plot because the y-axis, the range, the output, is scaled logarithmically. Now what that means is that instead of each line being 1 or 10 or 100 or 1,000, each line is 10 to a power. Now in addition, any sublines would also be divided the same way. So if we took that 10 to the first power and we drew 10 more lines in down here, those would represent 1 through 10. But then in the next section, if we drew more lines here, those would no longer be by 1, they would be by 10. So we have to keep that in mind. So example 5 says the population data of English Americans in the current United States for the years 1840, 1860, and 1880 are given below. Plot these 3 additional data points on the graph above. Now this is the same graph on the right. It's logarithmically scaled. Okay, so we're going to we need to break out a ruler. And this is fairly difficult to do, but keep in mind that the x, okay, is representing our years since, I forget what it is. Years since 1620, that's what it is. Years since 1620. That really ought to be written somewhere, okay? So, those 3 points we're being asked to graph since 1620, okay, because that's what this is. This is years since 1620, okay? So if we're looking at 1840, 1840 is really, when we look at years since 1620, that's not 1840, that is 220 on our current graph. 1860 is 240, and 1880 is 260. So those 3 points are going to be graphed on the 3 lines I just drew. Okay, then we also need to look at, we need to be very careful with where we're drawing these because our y's are logarithmically scaled as well, or our y's are logarithmically scaled, sorry. So when we graph these points, we need to make sure we get them in the right spots. Okay? And right now, we have this data here that has already been graphed for us. So now we're going to add 3 points to this graph. And those 3 points are these populations. Okay? So 17,069,453, okay? If we take the log of that population, that tells us approximately where to graph. So the log of 17,069,453 is approximately 7.2322. So when we graph that point, we go to the 220 line, we go up to 10 to the 7th, and we are just above that value, okay? This would be our 7.2322. Okay, then we do the next one. Well, 240 years after 1660, in the year 1860, which is 240 years after 1620, we have a population of 31,443,321. If we take the log of that number, 31,443,321, the log of that number is 7.4975. So we go and we graph this. It would be higher than the previous one because 7.4 is bigger than 7.2. Okay? It's also worth noting that we need to watch where we are in terms of our vertical height, because we do know that we have a 10 to the 8th power, okay? And really that point is probably a little bit higher than it should be. I'm going to move it down a little bit, try to get it better placed. 2.4. Okay, so 2.4 or 7.4, sorry, would be closer to 10 to the 7th than it would be to the next line, which would be 10 to the 8th power. Okay, next up we have 260 years after 1620. The population is 50,189,209. So if we take the log of 50,189,209, that is 7.7006. So we would graph that point. We still have not made it to 10 to the 8th power, but we are significantly closer. So that point would be closer to 10 to the 8th, but still not quite there. Please note that when you graph exponential data on a logarithmically scaled graph, generally speaking, that data will appear linear. And we will talk more about semi-log plots later in the unit.